You might be wondering why I put this picture up here for a very good reason. I just want to talk a little bit about what a partial derivative really means. So here's a surface. It's z equal to x squared, or if you prefer, we could have written it as f of x comma y equal to x squared. Right, same deal. We're just saying some function of two variables is equal to this. It's a cylindrical parabola. That's what that's called, or a parabolic cylinder. Sorry, it's a parabola, but it's been extended in another direction. And so when we have that kind of shape, we usually call it a such and such cylinder. So like a circle extended in another dimension would be called a circular cylinder, which, okay, whatever. Or an ellipse drawn out in another dimension would be called an elliptic cylinder, but they get called a cylinder. I don't know why. I didn't decide the naming. That's just what we do. So this is a parabolic cylinder, but what I really want you to see is that for this function, and I'll point out that the x direction is that way, and the y direction is back that way. It's kind of off kilter here. But if we move in the y direction, let me grab the right one here. If we move in the y direction, there's no change in the z value, right? No matter how far left or right we go, we can call that kind of left and right. But how far left or right we go, the elevation stays the same. On the other hand, if we move in the x direction towards you or away from you, the height of the function definitely changes. So what that means to me is that the derivative in the y direction should be 0 because there isn't any change when we move in the y direction. Whereas the derivative in the x direction certainly is not 0. Right? If we're moving back and forth in the x direction, the value of the output is definitely changing. So that's just kind of, I wanted to hopefully show you kind of on a picture or surface how you can see, oh yeah, if we're moving the x direction, we really are changing the elevation. And that kind of leads to most of how we deal with partial derivatives. So where's the thing? So yeah, so just to kind of put that down in words, if your function is equal to something nice and easy like x squared, then the partial derivative in the x direction, which you could write as f sub x, which we don't usually say the sub part, you say fx, or del f del x, that's going to be 2x. On the other hand, fy, or del f del y, is going to equal 0. Right? If we move in the y direction, the function value doesn't change. And while it's nice to have a good idea of what that looks like visually, as far as doing this practically, what we're going to do is we're going to pretend like the y is a constant. Or, I mean, sorry, no, yeah, there isn't even a y here. Sorry, but if there were a y, we pretend like it was a constant. Or when we take the derivative with respect to y here, we're pretending like the x is a constant. So the derivative of a constant squared is going to be 0. Yes. It means partial derivative. That's really the only difference. The only reason you write a del, which is just a curly looking d, is if your function is a function of more than one variable. You might argue here that it's not because it's only depending on x squared. But since we're considering it as a surface where y is still in play, you would really still write f of x, y, and you would still write partial derivatives. Right. You're always, if your function is a function of more than one variable, usually two in this class, but not always, then yes, you use the del notation. And again, nobody's really, or you can use this subscript notation, right? Whereas if we had written, say, like, if we were writing just f of x equal to x squared, we would write df dx is equal to 2x, or preferably f prime of x, right? That would be our notation for a function of one variable. Slightly different, but, and those, so look, I've written it really in a way you can't even tell. Is that a d or a del? Well, it is a d, but I didn't write it very clearly. Where these are dels. They're curly, but no one's looking for that. It doesn't really matter if you write a D or a del. Yes, you should know the difference, but you shouldn't sweat it. A couple important things to remember about functions. If your function is, say, like, I don't know, tangent of x plus 6, the derivative is going to be secant squared of x plus 0. Because the derivative of a constant on its own is just 0. But if your function is, say, 6 times tangent of x, the derivative of that 6 is not 0, at least not by itself, because it's a constant multiple. I would say the derivative here is the 6, let's write the derivative, g prime of x. The 6 hangs out, and the derivative of tangent is still secant squared. So constants on their own, their derivative is 0. Constant multiples of functions of your variable hang out. If you prefer, although you shouldn't, but you can. If you prefer, you could use the product rule and said it was the derivative of 6 times tangent of x plus 6 times the derivative of tangent of x, which still is going to work out to 0 times tangent plus 6 times secant squared of x. Yes, I can. But we really shouldn't use the product rule when it's just a constant times your function. You should just use the constant multiple rule. All right, let's look at some more interesting examples. Again, I suppose I could label today with today we're mostly dealing with partial derivatives. And I would say the main thing to remember is whatever variable you're differentiating with respect to, any other variable gets treated like a constant for that part of the process. Let's say our function is the following. F of x comma y is equal to, sure, x to the 6th plus 4y cubed plus 2x cubed y to the 4th. We're going to find 6 different derivatives here. We're going to start with just the first partials. So the first partials, meaning fx and fy. So the derivative of x to the 6th is 6x to the 5th. The derivative of 4y cubed, since there aren't any x's in there, that derivative is going to be 0. And then for 2x cubed times y to the 4th, the x cubed is the variable part. Everything else multiplying by it is a constant. So I'm kind of imagining the 2y to the 4th hanging out and taking the derivative of x cubed. What I'm really going to do is actually just think of it as 2x cubed. So I'm going to get 6x squared as the derivative of 2x cubed multiplied by y to the 4th. And then we would simplify and write it as just 6x to the 5th plus 6x squared y to the 4th. You don't really need to write that 0 in there. I'm just writing it to be extra kind of explicit about, oh yeah, this thing that's being treated as a constant has a derivative that is 0. Let's find the partial with respect to y. In fact, why don't you all find the partial? Oh, question. I would say we're taking the derivative with respect to x, but yes, exactly. We're moving in the x direction. Y is getting held constant. So the derivative of anything with just y has to be 0 because y isn't changing. And derivatives are all about how is this thing changing? Oh, it's not changing. Its derivative is 0.
And you take the partial derivative of like the last part.
Still keep the y. Correct, because just like in the previous example, when you take the derivative of a constant multiplied by a function, the constant sticks around and we take the derivative of the function. Just like here, the constant y to the 4th is sticking around and it's getting multiplied by the derivative of 2x cubed, which is 6x squared. So why don't you all try this other partial derivative if you haven't already. That's what I'm getting. Derivative of x to the 6th is 0. The derivative of 4y cubed is 12y squared. And the derivative of 2x cubed is y to the 4th. The 2x cubed hangs out. The derivative of y to the 4th is 4y cubed. So then we simplify that as 12y squared plus 8x cubed y cubed. Typically, we also usually look at second partial derivatives. So I'll point out, I could also write this as del f del x. This I could write as del f del y. Now we're going to find the second partials. Yes, I'm omitting the word derivative because people usually say we're finding the first partial, second partials, and we know it's derivatives. So here's how we're going to write the second partial. It's either del squared f del x squared, or you can write it as fxx. But either way, you're taking the derivative of our first derivative with respect to x. So we're taking the derivative with respect to x of 6x to the fifth plus 6x squared y to the fourth. Normally, I would write none of this. Normally, I would write fxx, I'd write that part equals, and then I would just take the derivative and get, what, 30x to the fourth plus 12x times y to the fourth. You definitely don't need to write as much as I'm writing in general when you're doing things like this. In a similar way, the second partial with respect to y. By the way, the reason this notation looks kind of funky is because what you're really trying to write here is it's the derivative with respect to y of the derivative with respect to y. That's why it comes out that way, where the bottom part is kind of like you're squaring the del y and the top part just squaring the del. It's kind of weird, but it is what it is. Or again, you can write it as fyy. We're looking at our fy, 12y squared plus 8y cubed y cubed. Sorry, 8x cubed y cubed. And then we're going to take the derivative of that. So the derivative of 12y squared is 24y. The derivative of 8x cubed y cubed, the 8x cubed hangs out. The derivative of y cubed is 3y squared. Again, not super important to simplify here, but I like simplifying when I can. 8 times 3 is 24. So that's my second derivative with respect to y. And then nobody's favorite, the mixed partials. Question?
Partial can be like first person, second partial, it's like first and second derivative.
Mm-hmm. So when I say first partials, I mean I'm finding all of the derivatives with respect to any of the single variables. Usually that's the partial derivative with respect to x and the partial derivative with respect to y, but it could be, right, you could have a function of 3 variables or 4 variables, and if I want to find all the first partials, I would take every first derivative with respect to every possible variable that's an input. Yes?
Why?
Mm-hmm.
Why? 8x.
So I want to point out, I didn't, so sorry. So right here, how do you go from here to there? Sorry, I interrupted your question.
They just combine the
Right, because what this really says is 2x cubed times 4y cubed, and all I'm doing is multiplying the 2 and the 4 to get 8, and then the x cubed and the y cubed just stick around as factors. No problem. So for the mixed partials, they're not any harder to find. The notation is kind of annoying. Here's what I mean by the notation is kind of annoying. You can have fxy, which means you take the derivative with respect to x first and then y second, which if you wrote it using the del notation would look like this. Del squared f del y del x. It looks out of order, but if you use this notation says you're doing the derivative with respect to y after you have done the derivative of f with respect to x. So we read from the inside out, we read from right to left, we do x first, then y second. X first, then y second. In practice, it's not hard to do. The notation is just a little bit wonky. So here, it's the partial derivative with respect to y of the partial we found for x, which was 6x to the fifth plus 6x squared y to the fourth. The derivative of 6x to the fifth with respect to y is going to be 0. The derivative of 6x squared y to the fourth is going to be 6x squared times 4y cubed, which is going to end up being 24x squared y cubed. Here's the good news. If you do it in the other order, it should come out the same. So our fyx, which is our del squared f del x del y, or del x of del f del y, which is del x of, our del f del y was 12y squared plus 8x cubed y cubed. If we differentiate this with respect to x, the derivative of the 12y squared part is going to be 0. The derivative of the 8x cubed times y cubed is going to be 24x squared, and the y cubed hangs out. And look, that's exactly the same. Bless you. Question. Are they always the same? You shouldn't know the answer. The answer is no. Better question. For what kinds of functions is the answer no? Really funky functions. If they're like the easy example of a function where this doesn't work is kind of super complicated. It's weirdly piecewise. So as far as you're concerned, if you see a normal looking function, meaning like f of x, y is just some stuff and it isn't somehow piecewise defined, you can be fairly confident that yes, the partial derivatives, the mixed partials calculated either way should always end up being the same. Yeah. So as far as we're concerned, we're not going to worry about them being different out of order. Questions?
Mixed partial, that they could be the same, but for the first partial, that.
Definitely not. No, they're typically going to be different because you're differentiating with respect to a different variable. The thing here is the mixed partial. If you do the derivative with respect to x, then y, or first y, then x, you should get to the same result. Ish, yeah, I would say similar, but it's more like you're doing one thing and then you do. It'd be kind of like if you took the derivative and multiplied by 5 or multiplied by 5 and then took the derivative. Either way, you're doing two different things, but you're going to end up at the same result. Let's look at more. Oh, question, yeah.
That's not next to the thing, the constant.
Exactly. Yes. Whatever variable isn't in the subscript here or in the denominator of your del f del whatever, that's the one we're worried about. And any other variable in there is going to be considered a constant. Let's look at something more complicated. Say we have f of x comma y equal to, sure, sine of x cubed times y plus e to the y to the okay, find the first partials. Find fx and find fy. Here, look. So our partial with respect to x, I see sine of something with x in, so that's a function. So I'm going to get cosine of whatever that stuff is. And I have to multiply by the derivative of the inside. X cubed is the thing, y is a constant. So I'm going to get, so times, geez, 3x squared y. That's the derivative of the inside part. Plus 0. So I don't even want to write that. For the other part, for the other partial derivative, fy, the derivative sine of x cubed y is going to be, again, cosine of that stuff. But then I have to multiply by the derivative of the stuff with respect to y. which is going to be x cubed times 1, plus the derivative of e to the y to the fourth is e to the y to the fourth multiplied by the derivative of the exponent, which is 4y cubed. And for problems like this, second partials start getting really ugly really fast. We'll do them here, but I just want you to see it's going to be gross. So let's find fxx. So I'm just going to look up here. I've got cosine of x cubed y times 3x squared. I'm going to have to use the product rule because I have a function of x times a function of x. So if we want, I'm going to think of this as like my u and this is my v. Just to remind myself of what I'm doing. So my product rule, it's going to be the derivative of u, okay, negative sine of x cubed times y times the derivative of x cubed times y, which is 3x squared times y. All that multiplied by the other 3x squared times y. Yeesh. So there's my derivative of u. There's my v left alone. And then we switch it up. We have cosine of x cubed y left alone, multiplied by the derivative of 3x squared y, still with respect to x, which is 6xy. So why is that there? All I'm really trying to say is be careful, right? It can be a little bit much to write when you're finding the second partials, especially if the first partials we had to use a chain rule for. Let's do FYY. Man, I feel like this HDMI cord is very, very sensitive. We'll try not to touch it. Okay. So for FYY, same deal. I'm looking at Fy and I'm just taking the derivative of that with respect to y. So for this first part, I don't need to use the product rule. I only have one function of y there. So it can be the derivative of cosine of some stuff, which is negative sine of x cubed times y times the derivative of the inside, which is x cubed, multiplied by the other x cubed that was still hanging out. For the second part, we do have to use the product rule because you have an e to the y to the fourth, and you have a 4y cubed. Let's call them a and b. So the derivative of e to the y to the fourth is once again e to the stuff times the derivative of the stuff. Leave the other stuff alone. That's your a prime times b, and then we switch it up. We go the other direction. We leave a alone, multiply by the derivative of b, which is 12y squared. Kind of funky. Yes, we could simplify this. No, I don't want to simplify it. Let's find one of the mixed partials, and I'll leave it to you on your own to show that the other way still gets you the same result. Good practice. So we'll find fxy. So we're taking the derivative with respect to x first, and we're taking the derivative of that with respect to y. So actually, I'm going to write this down. We're taking the derivative with respect to y of the partial with respect to x. Cosine of x cubed y times 3x squared y. I do have to use the product rule here because I have a function of y times another function of y. But it's not too terrible. So we're going to get the derivative of cosine of x cubed y, which is going to be negative sine of x cubed y times x cubed, multiplied by the other stuff left alone, 3x squared y, plus, and then we switch it up. We leave the first piece alone, multiply by the derivative of the second piece, which is, what's the derivative of 3x squared y? With respect to what variable? With respect to y. So the derivative of 3x squared y should be 3x squared times 1. So it's super duper important to make sure you're paying attention to the variable that we are differentiating with respect to. So on your own, you all should check that fyx is the same. Oh, yeah, we have do one more of these, and then we'll do something slightly different. So I should point out, if someone poses a question like this, yeah, let's say the following. Let's say we are written f of alpha comma beta is equal to alpha over alpha plus beta. And they say find the first partial derivatives. First and second. Right? They changed the variables on us, but we're still doing the same thing. We're just differentiating with respect to alpha and beta instead of x and y. So don't get thrown by a variable change. We like to use all sorts of things, especially in this class. I feel like a lot of other names get used for variables other than just x and y. There's a lot of t, there's a lot of n, so you gotta be comfortable with this. Good question. I didn't say the question that I said in my head, but the question I said in my head was, should we use the quotient rule or not? It's kind of a mixed bag. I'd probably land in the not and rewrite this as f of alpha comma beta equal to alpha times alpha plus beta to the -1. That's a totally fine thing to do before I start taking partial derivatives. Yeah, I can kind of go either way. I'm trying to think, what did I do here? No, I definitely did do quotient rule first. So let's do it that way. Even though I wrote that, it's still fine. Del F del alpha. I'm just using the quotient rule here. It's the bottom times the derivative of the top, which is 1, minus the top, times the derivative of the bottom, which is also 1, all divided by the bottom squared. I do think it's worth simplifying this. The top is alpha plus beta minus alpha. I should say, I think this is worth simplifying because I know I have to take the second derivative, right? If you know you're going to have to take a second derivative of something, it is almost always worth your while to simplify the first derivative as much as possible. So we would love to simplify this as beta divided by alpha plus beta squared, or probably actually as beta times alpha plus beta to the -2 power. Be careful that your alpha doesn't look too much like an x. Let's go the other direction. Del F del beta. In this case, I'm still going to use the quotient rule, even though the numerator is a constant. So I'm going to get the bottom multiplied by the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is still 1, all divided by the denominator squared. So this is just negative alpha over alpha plus beta squared, or negative alpha times alpha plus beta to the -2. Yeah, I think that's worthwhile. All right, let's find the second partials. Del squared f, del alpha squared. So I'm really just looking at this first derivative and differentiating with respect to alpha. So alpha is my variable, beta is a constant. So that beta that's multiplying out in front of this function is just going to hang out. And the derivative of some stuff to the -2 power, I'm just going to use the power rule and get -2 times my stuff to the -3rd. I should think about multiplying by the derivative of the inside, but the derivative of the inside is just going to be 1 plus 0. So I don't really need to write that down. And if I wanted to rewrite this in a more convenient way, I'd probably write it as -2 beta divided by alpha plus beta cubed. And the other second partial. Del squared f del beta squared. Okay, so looking at del f del beta, still feeling pretty good here because my function here, I don't have to use the product rule. This first derivative here just has a beta in that parentheses, so it's going to be the negative alpha is going to hang out, and the derivative of alpha plus beta to the -2, very much like last time, is going to be -2 times alpha plus beta, the -3rd, times 0 plus 1. Or, as I would prefer to write, 2 alpha over alpha plus beta to the 3rd. All right, yeah. They shouldn't match at this point. So I haven't even talked about the mixed partials yet. So let's be clear. The mixed partials are the ones that should match. The mixed partials being fxy and fyx. Those are the ones that should match. Those are the mixed partials, meaning we're mixing it up by taking the derivative with respect to each variable once. And what we're saying is the order we do that in doesn't matter. You can do x first then y or y first then x. You can do alpha first then beta or beta first then alpha. Let's go ahead and do one of the mixed partials here. Let's do del squared f del alpha del beta. Meaning we're doing beta first. I don't want to do that work again. I'm not trying to repeat my effort. So I'm going to look at my derivative with respect to beta and be like, cool, there's my del alpha del, my del f del beta, my derivative with respect to beta. So I know that I'm going to take the derivative with respect to alpha of my del f del beta, which was negative alpha times alpha plus beta to the negative second. And now I am going to have to use the product rule because I'm differentiating with respect to alpha, and I've got an alpha there and an alpha there. So I'm going to do the following. It's going to be the derivative of negative alpha is -1 times, leave the other part alone. If you like, we can use this u and v notation. There's my u prime. Leave v alone. It's alpha plus beta to the negative second. Switch it up. Leave u alone. It's going to be negative alpha multiplied by the derivative of alpha plus beta to the negative second, which is -2 times alpha plus beta to the negative third, multiplied by the derivative of the inside, which is 1. I know we don't need to really write that here, but in future examples, the derivative of the inside might not just be 1. It's good to be thinking about the chain rule kind of always. As before, I would encourage you, when you have a chance, check that the other direction of this mixed partial is the same. So you should definitely, when you have a moment, find del squared f del beta del alpha, or if you prefer, f alpha beta on your own. And see if it matches. Right. You can also have functions of more than 2 variables. So most of the time in this class, we're going to look at functions of 2 variables, but the idea of partial derivatives is extendable to functions of any number of variables, really. So, for example, if we had something like, sure, f of x, finger felt weird there for a second. F of x comma y comma z equal to x to the 4th times, sure, sine of 3y squared plus 4z. Now I want to find all the first partials. So there's going to be 3 of them. Fx, Fy, and Fz. I'm sorry, this HDMI cord. Did I break it? Sorry about that. 1 second. Yeah. Okay. Yeah, I remember not to touch the HDMI cord. It's very, very sensitive. So let's start finding these. Let me share my screen again here. There we go. Cool. So fx, usual deal. I've got x to the 4th times some stuff that doesn't have any x's in it. So the x to the 4th is derivative is going to be 4x cubed. And the rest of the stuff that's multiplied by it just hangs out. That's it. That's our fx. Fy, a little different. The x to the 4th, that's a constant, is going to hang out in front. But the derivative of this function of y, well, the derivative sine of some stuff is cosine of the stuff multiplied by the derivative of the inside stuff, which is going to be 6y plus 0. Right? There isn't any other piece there. It's just 6y. And then in a similar way, the partial derivative with respect to z, the x to the fourth is going to hang out. Again, the derivative sign of something that has our variable in it is going to be, well, cosine of our stuff multiplied by the derivative of the inside stuff. But now the derivative of the inside part with respect to z is going to be and then we could find all sorts of other interesting mixed partials or second partials, right? Someone could ask you to find something like f, x, x, y, where we do x first and then x second and then y third. We can totally do that. So for that, we need fx. We already have fx. Cool. So before we can do this, before we can tackle this, we need fxx. Well, great. fxx is going to be the partial derivative of fx with respect to x. Again, the derivative of 4x cubed is 12x squared, and the constant as far as x is concerned hangs out. So we get 12x squared times sine of 3y squared plus 4z. And now we can take the derivative of that with respect to y. So fxxy, our 12x squared hangs. The derivative of sine of some stuff is cosine of the stuff multiplied by, oh, sorry, no, that's right. Multiplied by the derivative of the inside stuff, which is 6y. Why don't you all try finding fxxz? Yeah, question. So we're imagining x to the fourth is like 3. So if you take the derivative of 3 times sine of 3y squared plus 4z, that 3 would just hang out in front, and the derivative of sine of 3y squared plus 4z would be cosine of 3y squared plus 4z times the derivative of whatever the insides are. So this x to the fourth here, as far as y is concerned, that's just acting like a constant. But I should be more explicit, a constant multiple. And as I've frequently said today, constant multiples hang out. They don't change, but they don't go away. Right, it's a multiple of something that has our function in it. Sorry, our variable in it. Yeah. You're welcome. So hopefully everybody's looking at fxx and trying to find fxxz. Yes. So I wanted 2 things. One thing I would encourage you not to use the word times there because we're not multiplying x, y, and x. That's just telling us the order. But the reason, but I'm not saying we couldn't actually. So you might be able to find fx, xy. It might be the same as xyx, but it might not. There's no guarantee about anything other than the mixed partials being equal to each other. If you mix the order up and do more than 2 things, I don't really know what happens, to be perfectly honest. So I would say it might work. I don't actually know if it works or not, but we're better off doing it in the way that we've been asked to do it. So even though it might end up being the same as if you did f, x, y, x, I would not. Let's see. So when I do fx, again, I'm only taking the derivative with respect to x, right? So as far as x is concerned, the sign of all this is a constant. Sorry, I can't quite see that. This whole sign here, as far as x is concerned, is constant. So I'm going to take the derivative of x to the fourth, which is 4x cubed, and then the sign of everything just stays. If I take the second derivative with respect to x, I get 12x squared, and the sign of everything just changes. And now I take the derivative of that with respect to z, I should have the 12x squared hanging out. And the derivative of sine of some stuff is, again, cosine of that stuff multiplied by the derivative of the inside stuff, which is now 4 since we're differentiating with respect to z instead of with respect to y.
The mixed partial derivatives, should we follow the order? So like x, and then y?
Yes. Now I will remind you, if it's written in the other Leibniz notation, the order is going to look different, right? The way you would write this using the Leibniz notation would be del cubed f del y del x del x. X first, x second, y third. Kind of annoying, but it is what it is. Yes.
Is there like, you have to write in the del thing or like X thing?
No, I don't. I mean, some teachers might prefer certain notation. I feel like this notation is usually what gets used the most because it's easier and faster to write. You can use either notation as long as it's correct, unless your teacher says you can't. Right? I'm not in charge, right? But if your teacher, both of your instructors should be fine with using either notation. They're both very universally accepted. Oh yeah, this interesting stuff. Sure, let's do that. So, what if instead of having a function of some variables, we have an implicitly defined function, meaning we have something like x squared plus y squared plus z squared equal to 3xyz. And I'm asked to find del z del x. So there's kind of two things going on here. One, well, if we're finding del z del x, what are we treating like a constant? Why, right? We're asking the question, how is z changing as x is changing? That's what this is really asking. When you say del something, or d something, you're saying how is the top thing changing as we let the bottom thing increase typically? Y is nowhere in this picture, so y isn't changing at all. So yes, we're going to note that one, we're treating y as a constant. And two, we are assuming z is a function of x. Otherwise, it doesn't make sense to ask the question, what is del z del x, right? If you're asking, what's the derivative of this thing with respect to this variable, we are making the implicit assumption that the top thing maybe isn't exactly a function of the bottom thing, but certainly depends on the bottom thing. So we can treat it like that. So, you guys remember implicit differentiation? Well, it's time to remember it. So we're pretending like z is a function of x. So if it helps, actually, yeah, I'm going to write this down for a second. So I'm just going to write down for a second. Instead of writing this, we're going to write this. So here's what we're going to you can write this down if you want to, but you don't need to really. I'm going to say x squared plus y squared plus, okay, z is a function of x. So it's some g of x squared equal to, sorry, not plus, 3 times x times y times, again, g of x. So now, if I were to differentiate both sides of this with respect to x, we're going to differentiate with respect to x. Here's what we're going to get. Derivative of x squared is 2x. Derivative of y squared is 0. The derivative of a function of x squared is 2 times that function of x to the first power times the derivative of the inside. Equal to, I have to use the product rule here. The derivative of 3xy is going to be 3y times the other piece left alone, plus, now we leave the 3xy alone, and the derivative of g of x is g prime of x. But really what we would do, instead of writing all that out, is we would just say, yeah, z is a function of x, and we differentiate with respect to x, we're going to get into multiplying by the derivative of z. So what we'd actually end up doing is saying, yeah, we're going to get 2x plus 0 plus 2z times del z del x equal to 3y times z, apologies, plus 3xy times the derivative of z. Those are the same, just using slightly different names and notations. And then just like with implicit differentiation, once we have differentiated both sides, we can then solve for the derivative by doing some algebra. So I'm going to collect this term and this term on the same side of my equation and everything else on the other side. I don't really care which side. Let's bring all the del z, del x's to the left. So I have 2z times del z del x minus 3xy times del z del x equal to 3yz. I'm going to subtract the 2x over there. Factor out a del z del x, you get del z del x times 2z minus 3xy equal to 3yz minus 2x. And finally, divide by whatever is over here to get that del z del x is equal to 3yz minus 2x divided by 2z minus 3xy. Just whenever you're asked to find some partial derivative of something defined implicitly like this, where we don't just have z as a function of x and y, we're just going to do the usual. Well, actually, we're not really going to do this at all. But we're doing this now to show you something cool in a minute. In a minute or in a day. Let's see. We're doing that next. No, yeah. So I would say don't worry too much about the implicit differentiation because we're going to revisit this example once we've talked about some other stuff. But it's not right now. Let's see how much I got 4 minutes. So yeah, that's a good place to stop. So you might ask a question like, what about an application? Specifically to biology. Well, let's go back and look at the BMI index thing. So let's remember our BMI example. So I'll remind you that the BMI of a person with their mass and their height inputted is their mass divided by their height squared. Again, mass is in kilograms, height is in meters. So you could ask a question like, how does BMI change if a person gains mass, but their height stays the same? So we're asking, how does this function change as mass changes? In other words, what's the derivative of our BMI with respect to a change in the mass? Well, that's not too bad. We could actually even write this function as just the mass times h to the negative second. So if we take the partial derivative of that with respect to the mass, it's going to be just h to the negative second, which is 1 over h squared, which I'll point out is positive. So if, not surprisingly, right, if the mass increases, the BMI is going to be larger. In a similar way, what if your mass stayed the same, but you got taller, which is less likely to happen in adulthood, but you know, right? So if your mass stays constant, but the height increases, well, then we're saying, what's the partial derivative of the BMI with respect to the height changing? And that's going to be, well, again, if I look at the derivative of this, the constant mass multiple is going to hang out. And the derivative of h to the negative 2 is negative 2 times h to the negative third. Or written a different way, negative 2 times the mass divided by the height cubed. The mass and the height are both positive, right? I mean, but so this whole quantity is going to be negative. Again, not terribly surprising that if we just got taller and our mass stayed the same, our BMI would decrease. You could also see this, by the way, just by looking at the function, right? If you look at this function here and the mass gets larger, the output's going to get larger. If the height gets larger, the output's going to get smaller. So that's not a surprise, right? But that connection should be there. We can be like, oh yeah, if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. That still holds true whether it's 17A or 17C. And Sure, I'll stop there. Yeah, question. Well, because I'm differentiating h to the negative second. So when I take the derivative of h to the negative second, I get -2 times h to the -2 minus 1, which is -2 times h to the negative third, or rewritten -2 divided by h to the positive third. Make sure you got your name on the sign-in sheet if you didn't already. And I have office hours in the map drop-in area from now until 4 p.m. So you got questions, swing on by. I'll be there for quite a while.